Today we are delighted to connect with Professor Michael Oldstone and the author of the book Viruses, Plagues in History, Past, Present, and Future. Welcome to Redera.
Thank you.
It's a fascinating time that we are having this opportunity to talk, and the book that you have has some really good messages as well. There are a couple of there are a lot of insights in the book, but one that really struck me is that there was a very simple sentence where he said there are animals, there are plants, and then there are viruses. Tell us how viruses are such a small organism, but they can have some profound impact, and how they've also managed to change the course of history.
Well, viruses are obligatory parasites. They need to invade cells. They can't replicate by themselves. They have to invade a cell and have the cell provide the machinery for them to make more progeny or baby viruses that are then released. But viruses are the only organism that can infect both plants and animals and bacteria. And when they do that, they sometimes can cause untold harmful effects. And that's what we've seen in humans, where viruses will infect our human initially, and that if the virus just infects the human, it's not spread by human to human, then usually the virus is contained. But if it then starts spreading human to human, you have problems of an epidemic or a pandemic that might occur.
Indeed. Would you give us some of the few examples of the viruses, especially in the last 200 years, recorded history of viruses, starting from smallpox and measles, that how they've affected the commerce, the life of people, and also the politics?
Well, I don't know if you have enough time to go over all of that, but if we start with smallpox, smallpox was present not in the New World, but in the Old World in Europe. And smallpox, when it broke out, killed about 35% of the people it infected. And like any acute infection, you either die from it or you survive from it. So if you got infected in Spain or England or Italy, 35% of the people died. And the rest of the people who survived the infection survived it for a long period of time. And smallpox at the time was an enormous problem causing a plague. So when the Europeans, Spanish and the Portuguese, came to the New World, they brought smallpox with them and decimated the native Indian population. So it's estimated that the population in Mexico was, let's say, about 14, 15 million, dropped down to less than 2 million because of smallpox. And that a very small handful of people, Cortez, who conquered the Aztec Empire, had about 500 conquistadors that were then reinforced by about 200-300, and he fought over an army of over 1 million people, and because of the outbreak of the smallpox, it decimated the Indians. Now the Spanish, who came over, were already immune to smallpox because they were the survivors. So when smallpox broke out again, which was brought by the Spanish, by slaves or other people, they were protected, and the Aztecs died. So the question was, why did these people who followed a religious group following a cross, went into battle, survive? Well, the Indians died, and they attributed it to their god, the European god, being superior to the native god or gods, and that led in large part to the conversion of Christianity in the Americas. Then on top of that, at the time when the Spanish colonized, there was a religious debate whether the natives had a soul or not. If they didn't have a soul, they could be worked as a beast of burden, and the Spanish did that. So a lot of the natives who worked in the mines and other places like that died from overwork and starvation, and also from disease. About 40, 50 years after the Spanish initially came, a Franciscan named Dukakis managed to convince the church authorities and the king of Spain that natives did have a soul, so that they stopped using them as beasts of burden. And then if you have a soul, you can be converted. Now, because so many natives died, they then had to bring in replacements. And so they brought in Africans as replacements. So the slave trade came because of Africans being brought to replace the Native Americans who died from smallpox. Now, when the Africans came in, they were exposed to a disease called yellow fever. It was a frightening disease. Once again, killed about a third of the people it infects. And that was never seen in the New World before. And so when the African slaves came in, they then brought with them yellow fever. And yellow fever then started to decimate not only the natives, but also the Spanish, who hadn't seen yellow fever before. So really a quick of a history. And then if you follow that logic or follow the history further, the French were colonized the New World, as did other countries, usually because of their crops, mostly sugar, which was then a commodity that was in short supply and was a very valuable commodity. And so the French were in Haiti and had large plantations in those places. And there was a revolt in Haiti against the French, and Napoleon sent his brother-in-law with a large army to put down the rebellion. Well, about 80% of the French troops that were sent died of yellow fever. And Napoleon then decided that he couldn't afford to keep an army in the New World. He already, in addition, of course, to Haiti, owned a good part of what was to become the United States, because the French had colonized New Orleans and part up the Mississippi River. And then, as you know, Napoleon arranged for the Louisiana Purchase that Thomas Jefferson bought. So an enormous Louisiana Purchase, enormous land, was bought by the new American Republic, the colonies, which did two things, which gave them a way to expand westward, number one, and number two, prevented any difficulty in their expansion against the French. So that basically is just an idea of how these infections occurred. Okay?
Fascinating. It had so many implications. The French, so-called, gave up the whole idea of domination or expansion in the what we call now United States, or the New World at the time, and the United States was able to continue its expansion on the westward, and at the same time, the Louisiana Purchase was in many ways happened because of the outbreak of the virus that 27,000 soldiers that was sent by Napoleon couldn't resist to.
Right. So that shows you how viruses have affected the history of commerce. They infect the history. They affect politics. They affect business. They affect rulers. And viruses. There are no boundaries for viruses. Viruses just pass across countries, and viruses have no prejudice. They can infect kings as well as slaves, and so they're equal opportunity parasites for that on that basis. You have to realize that the first viruses, the virus infections were recorded at the time of Hippocrates, so that's 4000 BC. That one did not isolate a virus or show that there was a virus until the late 1890s. That means when viruses broke out, like yellow fever broke out along the Mississippi River, people had no idea what the cause of why people were dying. Same thing with smallpox and yellow fever, etc.
Can you walk us through a very basics of principles of virus infection and its course? And there's always some vector involved in it as well. If you can give us some basic understanding as a refresher.
Well, just to simplify, to make it short, viruses based on the nucleic acids are either RNA viruses or DNA viruses. That is RNA nucleic acid or DNA nucleic acid. And so the DNA viruses would be like herpes viruses, would be an example of the DNA viruses, are very large viruses. And when they replicate and they make errors, because viruses mutate and select all the time. So the DNA viruses, when they replicate and make a mistake, they have a proofreading device that picks up the mistake and throws out those bad viruses. So therefore, DNA viruses are quite stable, can get to be quite large, and they contain maybe anywhere from 200 to, let's say, 400 genes. Smallpox being an example of a DNA virus, along with herpes simplex virus or cytomegalo virus. Now, these viruses that have a lot of genes, let's say 200 to 400 genes, the largest viruses, and they only need about 15 genes for their replication. And the other genes that they carry are accessory genes that give the virus a better ability to replicate. So, for example, smallpox has an accessory. Smallpox infects the skin and lung and blood. Let's look just at the skin. So smallpox has a gene that encodes for the growth of new skin. So if the smallpox destroys some skin cells, then the virus is making additional skin cells for the virus to grow in, and so forth. So one other aspect of virology is that realizing this occurs, commercial companies have isolated, let's say, the gene from smallpox or similar genes like that make products that are going to be useful for human health, and added that to the pharmacological armamentarium that we have. So those are the DNA viruses. So they're reasonably stable and they're very large. In contrast, the RNA viruses are much smaller, and that's because they mutate, but they mutate at about 10,000 to 100,000 times more frequently than the DNA viruses, because they don't have any proof mechanism that will remove the viruses that have mutated. So in RNA viruses, it's sort of a survival of all the mutated viruses that are present, and the strongest virus is the one that survives. And that's why the RNA viruses are like influenza measles, HIV, even the coronaviruses. So the RNA viruses are the ones that are constantly mutated and being selection. Common cold virus, another example. So they're very small. Because they mutate so much, they can't have a large genome like DNA viruses do. And so these viruses have different mechanisms of how many genes they have. Now, all viruses need to have an outer coat that has to attach to a factor on cells that it infects, and that's called a receptor. So it has a way to enter into the cell. And once it gets into the cell, then the virus has to uncode its information and to replicate using the machinery of the host to make more infectious virus. So that in terms of thinking about ways to counteract viruses, one is you try to make reagents that will limit the virus's ability to attach or enter a cell. So one way that's done is if you vaccinate people or you have a natural infection, you make antibodies, and the antibody would be to the outer coat of the virus and prevent it from binding to its receptor to get inside of the cell. So that's one way. The second way is when the virus gets into a cell, it uses the cell machinery to replicate its own progeny, or its own more babies. And if you understand cell biology, molecular biology, you can see the parts of the cell that are necessary for the virus uses to make more viruses. And then you try to make materials that are antiviral that won't kill the cell but will prevent the virus from replication. And that's called antivirals. And finally, when you have a viral infection, in addition to eliciting antibodies, which protect the viruses from binding and also block the viruses in the fluid phase, you generate what's called killer cells or cytotoxic T lymphocytes. And their function is to recognize a virus-infected cell, usually early in infection, and to lyse or kill that cell. So the cytotoxic T lymphocyte prevents the factories that make more infectious virus. And so you need immunity and antivirals to attack and to control virus infections. And then viruses depending on the tissue they infect. A virus that infects the skin is inconvenient, etc. But a virus that infects the heart and kills heart tissue is a dangerous virus. Or a virus that infects the neurons in your brain, that's a dangerous virus compared to one that infects, let's say, just skin. So it depends on where the receptors are and where the viruses go. And in terms of viruses, you get acute virus infection and you get infected like with smallpox, or as a good example of it, you either die from it or you survive from it. If you have a virus infection with an RNA virus, like, let's say, like
coronavirus.
Well, coronavirus is an RNA virus, but are really thinking that there are RNA viruses that can cause a persistent infection, like or chronic infection, like HIV, and then that's a different situation, because then the virus survives in its host for a long period of time. You know, sort of a virus that causes a chronic infection is like a virus on welfare. You know, it just lives within the host, doesn't have to look for a new host to infect. Now, a virus like the coronavirus which is an RNA virus, or like smallpox, which is a DNA virus, keeps on needing susceptible people to infect. So if you remove susceptible people from the virus, it will eventually die out because there are no more people for it to infect.
Do we know what
Does that
gives...
answer your question?
Yes, yes. Do you know what gives the virus the ability to mutate, and do we know that can we stop the viruses from mutating?
Well, the virus has to replicate, and when it replicates, it keeps on making errors in its replication. That's normal for any cell to do that. When it happens to just a normal cell and you make mutations without a virus that occur, you can get cancer, right? So what happens is the virus just mutates, and with the RNA viruses, you don't have a proofreading system to eliminate the mutants that are made, and so you wind up with lots of mutant viruses that are changes in the nucleic acid, different bases of nucleic acid. And like a gym, they all compete for survival. And the one that is the most fittest then gets out, and it's the virus that you wind up with. So that's what happens. The DNA viruses also mutate, but there's a proofreading frame, and as I mentioned to you, therefore, the mutational rates are between 10,000 and 100,000 times smaller than an RNA virus is. So you have different clinical findings between RNA and DNA viruses, the general rule.
Indeed. Switching back a little bit from the science to the history again, how viruses were recognized as danger to health, because that was very fascinating to read in the book, that there were a lot of misconceptions, misleading views, and faith and mysticism, all that was involved. If you can sketch a little bit of that how eventually viruses were recognized as danger to health.
I will tell you that. I also will tell you that a new edition of the book is now being set in type, which brings it up to date, including the COVID-19, and expands on the book. So you might mention that, which you're right, huh?
Sure.
That's coming out by Oxford, the same people who published the other book. Okay, so let me tell you what happened. When infectious diseases occurred, nobody knew what they occurred from. They thought they were the wrath of God, depending on your religion. And but all religions more or less thought that this was God's punishment for something. And in fact, if you think about it now, we have some people, for example, some pastors that I read about in Louisiana, who felt that this is God's displeasure with the COVID-19 virus, and have held open church services to say we have to worship, and believe in God, that by not believing in Him, we have more disease. That's been a common theme through history as well. Well, so nobody knew what the cause of any infectious disease was. It was a mystery. So maybe it was in the air. That's called marasmus. Nobody knew what it was due to. And then in the 1840s, Louis Pasteur, who was the founder of microbiology, definitely showed that there were microorganisms that caused disease. And he did that with bacterial diseases. That is, he took a disease, let's say a rancid meat or chicken fowl or some disease, and he then took that material and he put it on a large filter and put it under pressure, and that the material got stuck on the membrane, that was a bacteria. And so he showed that it was bacteria that could cause disease. And then following Pasteur, a German, Robert Koch, then showed by Koch's postulates that the material that was on the filter from a disease, let's say diseased animal or diseased plant or diseased meat, could then be inoculated back into that substance and cause disease again. And that was called Koch's postulates. And so one knew that that's how bacteria work. But then about the 1890s, first starting with the tobacco mosaic virus, there's a outbreak in tobacco plants that occurred, and a Russian botanist or Russian scientist showed that you could take material from the tobacco plant and put it on the Pasteur filter, as it was called, and it didn't stick to the Pasteur filter, but went to the bottom of the flask. So that meant it was too small to be caught in the filter. So it was much, much smaller. And they didn't know what it was, but they could show it was not a toxin, because if it was a toxin or a harmful material like that, then as you took the material at the bottom of the flask and diluted it out and re-inoculated it, eventually you would lose the infectivity, because a toxin doesn't replicate. Or the material they took from the bottom of the flask, once again, which was invisible, and then they diluted it out and continued to replicate, because you have replicating agents who continue to get disease. So first it was done in a tobacco plant by a Russian named Arbanovsky. Then it was done in Holland, also by Benedrek of the tobacco mosaic. And then two Germans looked at foot and mouth disease virus of cattle in Germany and countries around Germany, and the isolated foot and mouth disease virus once again went through the filter, was at the bottom of the filter, and that when you diluted it out, still could cause infection. Those are the very late 1890s. And then the first human virus was isolated by Americans, and that was done by Walter Reed and the Walter Reed Commission and three other people who went to Cuba, and that was with yellow fever. And they showed the same event with yellow fever. And if you think about it, how smart these people were. Remember, the viruses were so small you couldn't see them, because when you first could see viruses was by electron microscopy, and that's in the 1930s. So that's 35, 40 years later than they did their experiments. Second, we didn't know the viruses had nucleic acids. That's in the 1950s. So this is really, if you think about it in the span of history, it's quite an accomplishment over a short period of time. And then the isolation of viruses followed just the Pasteur model, which Pasteur-Chamberlain filter, and that if you had an infectious disease, let's say polio, you found polio, you just put it on the filter and see if it got stuck on the filter with bacteria, and it passed to the bottom of the filter and you couldn't see it. It was likely an infectious agent, and then you would re-inoculate it. Of course, if it was a human disease like polio, you didn't re-inoculate it into humans, you inoculated into other animals, and if you inoculated into the right kind of monkeys, you would reproduce the polio effect. So that's how viruses were initially found. Later on, in the 70s and 80s, we have different ways to look at the RNA and DNA by sequencing, and we have molecular and cell biology to identify them, and different fluorochrome dyes to identify them, and cell culture to identify them. So the technology is very different now.
Indeed, but these scientists persevered despite the mounting criticism and continuous distractions and sometimes a lot of political interference, and still found a way to actually not only identify them but also isolate them and then also find the cure. In some cases, also find the vaccine as well.
Correct. But then that aspect of it is common today, isn't it? I mean, when you have the dispute between science and culture, usually culture always wins out. When you have a dispute between science and politics, then it's difficult for science. Look at the early days of the COVID-19 outbreak, of what happened in terms of the politics. I mean, it wasn't announced from China because if you announce an outbreak of an epidemic, you prevent tourists from coming in, you prevent businesses from coming in. And you know the story that happened there when the first doctor raised a suspicion that it looked a lot like SARS as a virus. You know, he was harassed and forced to write a confession. So that hasn't changed very much, has it? And then you have people who fight against vaccines, even though we could completely eradicate measles. You can't do that because you have people who culturally and other reasons don't want to be vaccinated, and put all of us at risk. You might think about a virus related to measles in the same family is called rinderpest, and it affects cattle. And rinderpest is the second virus that's been eliminated from the universe, smallpox being the first. So you could ask the question, why was rinderpest eliminated and not measles? And the answer is very simple. You don't need the permission of the cow or the cow's mother to vaccinate a cow.
You have a fascinating sentence in the book where it says, when culture and politics collide with science, science always loses until the disaster strikes. And there's a cowpox, as you were alluding, was a famous example of the resistance to vaccination.
Sure. So that there have been things like that. Once you have an epidemic that frightens people, then science plays a dramatic role. So if you were old enough to live as a child through the polio scares, when there were anywhere from 30,000 to 50,000 children who got polio in the United States and were paralyzed, then there wasn't any question about vaccination. I mean, the people were very supportive of science, quite dramatically. In fact, the polio vaccine and the polio fight was done predominantly by private people donating money to the March of Dimes. And you probably know the March of Dimes got its name because some mothers in Arizona marched in the neighborhoods to collect dimes for research against polio virus. So that when the virus affects you directly, it's a scare. If you're worried about your child, obviously that becomes a great scare.
There's a fascinating story in the book about Memphis, Tennessee experience during the 1870s. That how the yellow fever struck. And what is fascinating about that is the response of the people, the government, institution, and the commerce was exactly what we see today in the current time of coronavirus here.
Yes. It was the same, wasn't it? And about not to worry, that just everything is going to be all right. Even though, if you read the history of yellow fever when that broke out, it was followed in the newspapers. It's from the Caribbean up to New Orleans and to towns along the Mississippi. So New Orleans had a devastating death rate to yellow fever. Then Vicksburg had a devastating effect from yellow fever. And Grenada had a devastating effect from yellow fever. So up on the line, next ship coming, paddle boat coming up was to Memphis. And the business interest said, well, if we close things, if we prevent commerce from going on, it would be bad for our business. And so that's how yellow fever came. And as you recall, Memphis at the time of the outbreak was one of the most, except for New Orleans, was one of the largest cities in the South and was a greater municipality in terms of commerce and growth than Atlanta at that particular time.
Cotton capital.
In terms of cotton and trade and trains and et cetera, et cetera. So Memphis had a population of over 40,000 at that time. And when yellow fever struck and started to kill in Memphis, about half the population left, fleeing. And frequently they were met on the borders of other states like Arkansas by vigilantes with guns to prevent them from coming across. And of the 20 or so thousand people who stayed in Memphis, about 12 to 15,000 died. So, and then Memphis really never recovered in terms of the commercial dominance it had. I mean, obviously it's a commercial and vibrant city now, but in terms of being a metropolis of commerce in the South, as the major one outside New Orleans, it never recovered. And you should also know that because of what happened with yellow fever when it occurred, one didn't know about it was a virus. One didn't know it was passed by mosquitoes. All they knew was that it occurred when the weather was warm, and when the frost came, it disappeared. And I think the chapter on yellow fever relates very well to the fear of the people who died and the reporters who came down to report at what was going on. It turns out about in Memphis about bodies being stacked in the streets to be picked up. That's really something, isn't it? And then if you go into influenza in the United States in 1918 and 1919, in the city of Philadelphia, they ran out of bodies. They got too many bodies and ran out of coffins. They had to bury people in pits. And if you go earlier in history to smallpox in England, they buried people in pits as well because they ran out of coffins. And now you look on the news and you see the refrigerated trucks in New York being loaded with coffins, and in Italy,
and in China and in Iran,
so
the response is same.
That's right. That's right. Around the world. That's right. So what you know is that these infections and these pandemics are not going to go away. They're going to occur and reoccur. And you know that the majority of them are passed through animals into humans. So COVID-19 is passed by bats into a cat-like animal called a civet, and from the civet it infects humans. And then if you have human-to-human spread, which happens with COVID-19 and happened with SARS, then you have a pandemic that occurs. And so you ask the question: if these are going to continue to occur, if humans are going to keep on encroaching on places where exotic and other animals live, you can expect more and more of these to come. I mean, HIV is an example of a passage. In our recent lifetime, the SARS and COVID-19 are an example. Influenza is spread by birds. That's another example. So that the lesson is, you need to be prepared. You need to put aside and support basic science that can work to uncover and to rapidly do things. We can now rapidly screen genetically to find the viruses are mutating. If we have another kinds of ways, we have techniques now for looking at molecular things. We need to sustain those things, not just react with them when an outbreak occurs again. And most importantly, we need to have surveillance systems, knowing that another one will come back again. These things continue to come. And we can't have governments that say, well, you know, we support a pandemic group because of SARS may be, and then SARS disappears, well, let's disband the group. Then Ebola comes, we form another group for advice, and then Ebola passes out, before it reoccurs again, we disband that. And now we're going to have a COVID-19. We need to continue to have strong public health and monitoring for all these things. And then we need the governments to understand that. I mean, isn't it ludicrous for you to know that you can prevent measles? And it's not that it's just a childhood disease, but 1 out of every 100 people get infected with measles get brain problems, and about 1 out of about 400,000 get to be institutionalized because of that. So how can you, and you have a vaccine that can prevent that completely. How can you not vaccinate people? How can you have ignorance of people not wanting to do it? And how can you have people who know about quote unquote herd immunity and say, well, I don't have to vaccinate my kid? I mean, you know, the whole thing is just ludicrous. If you could in fact have a leadership in government, and I'm not talking as a Democrat or as a Republican, I'm talking as a humanist and as a virologist and immunologist. If you could have a government that was devoted to preventing or being on top of these diseases as they occur, you wouldn't be having what we have now with COVID-19. You know, and it's what you're seeing is not just the problems of the United States and of China, but it's of many countries. Many countries.
Absolutely. Just as you were saying, just to draw some numbers again, which you highlight them very well in the book, smallpox killed 300 million people, more people than the wars during that time all combined. HIV infected about 39 million people and killed 17 million. Measles, 130 million infected and killed 8 million. And yellow fever, which most people may not recognize or even remember, that in 1793 it forced the U.S. government to shut down in September.
Right. That's right. They all left the capital. It's quite amazing. And then look what happens. Yellow fever is a disease you won't be able to get rid of because it's a disease that the mosquito passes in the jungle to monkeys, right? So the way you get yellow fever now is by going into the habitat where yellow fever is. Okay? Now what happens if a person decides to go on holidays in Brazil and decides he wants to travel down the Amazon River for a bit and doesn't get vaccinated against yellow fever and gets bitten by a mosquito? And there's incubation period of several days. And with the rapid transportation now, you get an airplane and in 4 hours you're back into the United States, right? Now you're carrying the yellow fever virus and it's incubating in you. And let's say you go back, this happened in Tennessee not too
1996.
long ago. Yeah, and then there are the mosquitoes that can spread the yellow fever.
Yeah, the yellow fever reappeared in Tennessee, in the United States, in 1996 after 70 years, as you mentioned in the book.
That's right. That's right. So that's right. But it didn't spread to the entire population, which of course it couldn't. It could have because people are not vaccinated, right?
Correct.
So and of course you don't have to be vaccinated unless you go to Brazil. But the guy who went didn't get vaccinated. Zika is the same thing, isn't it? Zika, somebody went to Haiti and then came back to New York and had this mysterious infection with fever, and they thought it was dengue fever, which is a mosquito-borne disease that we know about. Nobody heard of Zika. And then he had Zika. He spread Zika. And then you talk about Zika that occurred in mostly the Caribbean and the Central American countries. I mean, it caused, brain disease. I mean, there are going to be thousands of kids who will be mentally impaired because of the virus infection. So that I think we have to realize that these infections will be with us for a long time, that the ones that we were able to control, like measles, we should completely control. Polio dramatically has been reduced to a very small number. Whether we can ever get rid of polio completely, I'm not sure of, because there are people who carry polio virus or immunosuppressed and secrete it into our storage system, and it's an oral anal disease, and most people go swimming there, other things, it's in the pool, so you can really drive polio down to from hundreds of thousands of cases to what is it now, about 1,000 cases, and sometimes lower than that. So you can do all those things, but you have to be vigilant. You have to have good public health. I mean, you need to have good science to continue to fight these diseases. What happens is that government and politicians say, well, this disease hasn't broken out, this pandemic, I don't need this pandemic committee, and I can invest $10 million in another area that needs some support. And that's basically what happened. If one was to look at it very hard, it's not only the Trump administration that disbanded the pandemic part, but there was the Bush administration, the Obama administration, So it's at that level.
It is sad in many ways, and yet it's very fascinating that we would try to save $10 million or $20 million for the research, and then we would come up with $2 trillion of stimulus.
It's incredible, isn't it?
Incredible,
isn't it? And it tells you also that why are you cutting support as has been cut for the last 10 years? Well, I've been in this game for research in the NIH. Why would you cut those funds? I mean, NIH is well supported. Is supported well, but they're funding now something like 10-12% of grants that come in. I would say that about 20%, 25% of grants that come in are worthwhile. That's my experience in terms of being on sections that review grants. About 20-25%. but you're not funding 25%, you're funding only 12%. So, so a lot of grants that should be funded are not being funded. I wouldn't argue that there are some grants that make the 12% funding that should not have made 12% funding. But, that's a small error.
And yet not
so
a single minute.
Society that invests in its future will have a rosier future.
Indeed, yet not a single word. Yes, go ahead, please.
Think about it. Think about it now. I mean, a colleague of mine and a person I know, who I know personally, Tony or Anthony Fauci, head of National Institutes of Allergy and Infectious Diseases, has been leading the fight as he did against anthrax, and against Ebola, against HIV, and is now against COVID-19. And yet he's being attacked, politically being attacked, isn't he? He's not a politician. He's been politically attacked by a number of people. When you think about it, it's just outrageous.
You brought up a phrase earlier about herd immunity. And you have a little bit of insight as well in the book. There's a different level of herd immunity is needed for different kind of viruses. Can you give us a few examples so people can understand what it means and why it plays a role, what role it plays, and why different level of immunity is needed?
Well, if you have a population that has never seen the virus before, it's a susceptible population. And then all the people who are susceptible can be infected and harvest the fruits of that infection and that disease that occurs. Now, if you go ahead and you have immunity either through natural infection or through vaccination, if you vaccinate, the whole purpose of vaccination is to prevent natural infection so that you don't suffer and have the consequences of severe disease or death. So you vaccinate people. Well, as you vaccinate people, you get a group of people that are immune to that virus. And those people who are immune become, you recall they say they are a herd that are immune to that virus. Now, different viruses have different infectivity rates. So, for example, if you look at measles virus is probably the most infectious virus. It has about a 98% infectivity rate. That means if 100 people were in a room who had never seen measles before, and you introduce measles, that 98% would be infected. Well, if you now vaccinate the population so that you get about 90% that are immune, then measles virus has problems finding a susceptible person to replicate in. And you can get rid of measles virus. So that's what herd immunity means. Now, other viruses, let's say some other viruses, let's say smallpox, or let's say influenzas, it may be only 40 to 60% herd immunity. So you have to continue to either eliminate the virus, like smallpox was, or you have to revaccinate, like you do with influenza, as it changes all the time. So any public health person tries to get as many people out of the susceptible group into a herd group that are immune to the agent. And that way you can limit or make it very unlikely to get another infection.
Indeed. You also have a nice explanation in the book, which you can summarize it, that it's one thing to know what the virus is and how it spreads and how it its ability to cause disease, but it also our human system combats viruses, and there are different ways it does. So maybe if you can explain how the human system combats these virus attacks.
Well, I thought we did that a little before. When you get infected with virus, the first thing you get is called innate immunity, and that's the rapid response immunity that takes place immediately over the first 3 or 4 days. And that consists of some small molecules like cytokines, like interferon, which are released from cells and protect other cells from being infected by a virus. And there are cells called natural killer cells, and there are macrophages and other cells that initially come in contact to try to limit the infection. But the major players are the adaptive immune response, and that is the humoral response and the cellular response. The humoral response are antibodies, and their effect predominantly is to get rid of viruses that are in the fluid phase or prevent the virus that's in the fluid phase from attacking or attaching to the receptor. And once the virus gets into a cell and replicates, then you need the other arm of the immune system, which is called cell-mediated immunity, and that is mostly cytotoxic T lymphocytes, and they attack the infected cell and they destroy it. Now, they have the ability to recognize some viral parts of viruses that are put on the surface of cells before the whole virus is made, so they can attack a cell and remove it before the progeny virus is made. I would guess, or I would imagine, that in COVID-19, as in most virus infections, it's the cell-mediated immune response that is responsible for preventing the acute spread of virus, and that the antibody response comes in later. Now, it's maybe a little more complex than I mentioned to you, because if you have a high viral titer, an antibody reduces the virus titer, then the cell-mediated response is more efficient and effective in working. So just by evolution, all these responses are important, and they work together. But you can demonstrate where one maybe plays a bigger role than the other one plays a role.
The history of virus and virology is also the history of men and women who work together, and medical investigators rather, have linked certain disease with specific viruses. And I think you, in the book, weave along very well not only the science, but also the people and the personalities that actually fought it often individually to find and advance the science. Would you explain one or two of those personalities so that people can understand, or the listeners can get a better appreciation of, like Jonas Salk or others, or Walter Reed, as you mentioned, who played a very pivotal role over the last 200 years?
Well, scientists are humans, male and female, so they have their own conflicts and prejudices of what they do. I think most scientists prefer to work as workhorses, that is, move the field forward. Some want to be racehorses and want to win a race to something that occurs. I've had a great advantage in that I've started my career during the golden age of medicine and of pathology. So a lot of people in the book I know personally. Some of them some as colleagues, some as very good friends. I spent time with lots of them on a social basis. So I've been involved with a lot of them. Obviously not with Walter Reed, it was way before my time, but with the polio people, yes, and with the current people with COVID-19, and with the influenza people I have. In terms of the polio virus, that's where you have, and the HIV, and that's where you have the most intriguing personalities that occurred. With the polio virus, once it was realized that you had to make a vaccine against the 3 strains of polio, making a vaccine not against one of the strains of polio, and you had people trying to make the 3 go against the 3 strains. And then there were 2 hypotheses of the best way to go. One was by Jonas Salk, who felt that you should inactivate the virus, and so the virus could not replicate, and give the virus that way. So that's an inactivated system that Jonas Salk pushed. The other 2 virologists involved, major virologists, were Hilary Kaprowski and Albert Sabin. And they wanted to have an attenuated virus. That's sort of what Pasteur first found with rabies. That is, you weaken the virus so that the virus doesn't cause a severe disease, but causes a very mild disease or an apparent disease. The advantage of the attenuated virus is that it's a replicating agent, so it gives you much more material to make an immune response against than does the killed virus that you inoculate. So most virologists would like to use attenuated viruses if they can. And so there was a competition or people between Sabin and Kaprowski. They both were major contributors, and they both had their own personal feelings about each other, which I don't want to go into, but a little bit is in the book. It's very interesting, isn't it, for me which I didn't really put in the book for different reasons, but it's very interesting to me that all 3, Sabin, Kaprowski, and Salk, were Jews, that they came from immigrant families, which also speaks to the United States as a place that captures not only the musicians like George Gershwin, but that captures the scientists that come in and are able to do great things. Even in measles, that was done by a man named Goldberger, who isolated measles, was a first generation from Hungarian refugees. So that speaks also to the attraction of the United States and the advantage the United States has to increase and use great resources in terms of people. The people provide those resources. And then with polio, there was a conflict between Robert Gallo, who was at the NIH, who's a very good friend, and Luc Montagnier in France about the isolation of the virus. Certainly a lot of us felt that with a Nobel Prize going to Luc Montagnier, it also should have gone to Bob Gallo, because they both were very, very important with HIV. Gallo was extraordinarily important, not only for HIV, but also for developing the test against, to tell who had the test against HIV, which protected our blood supply, etc. The test was absolutely essential. So there are those conflicts, but overall, those are minor to getting the accomplishments that were done. So the way I would summarize that is that all those people should have received the laurels of society and humanity any way that it's given out. As Walter Reed and his three companions should have, which one got extraordinarily sick and one died, to prove that yellow fever was spread by a mosquito and it was a bloodborne disease. As you know, one person died from that group. It was self-experimentation. I mean, those were shining examples of what immunity, of what humanity is all about.
Indeed, and there are also brave souls right now on the front lines fighting the COVID-19. In your opinion, in your vast experience, what do you think the scientists have the challenge right now to come up with the vaccine, and where do we stand on it?
Well, I don't think it'll be hard to make a vaccine. The question, what you need to do is to have a vaccine that's safe. So what you need to do is make a vaccine. Then you have to show that the vaccine works, and to make it work, you have to do it in animals, and show it's protective. Then you have to go into human volunteers to show that it's not toxic to volunteers, it's safe to take, and that you generate the immune response that you need. I would argue very strongly that you need both humoral and cellular immune response, but not all of my colleagues would agree with me. They would think just humoral response, but I don't agree with that. And then once you do that, you have to see if the vaccine will work. Now, if I'm told that the majority of people that are infected in the United States with COVID-19 have not been tested, and so we don't know who has been infected or not, or who's immune. That seems to be the case. We don't know that. We just know, are the people that have been tested, we know who has it or doesn't have it. But we don't know for the vast majority, right? So then if I give a vaccine to somebody who's already immune to it, the vaccine's going to work, isn't it? So I need to know all that information to make sure a vaccine is safe. So that's why it will take maybe a year to do the safety requirements. You certainly don't want to get a vaccine that will harm people. Because then what you do is you give ammunition to all other people against vaccination and against support. I mean, you don't want to be harmful. It's sort of the war or the creed of Hippocrates. You know, physicians must not harm patients. So it's a safety issue.
But if we are away from 9 months to 16, 18 months, somewhere in between, how do we function as a society until the vaccine comes? And if it's airborne and it spreads from human to human, what do we do between now and...
Since it's airborne, if you separate people, you might expect in it's done well, you might expect in 4 to 6 weeks that the usual down curve will happen. Also, antivirals are being developed. You know, smallpox is eliminated by a vaccine, but currently we have antivirals against smallpox, which were not made at the time that the virus was eliminated, which were effective against it. So I think that that's a possibility. The other possibility is that the virus itself can induce molecules from a person, from a host cell, and these molecules in themselves may be quite harmful and may lead to the disease, the severe disease that occurs. So you can make drugs against those molecules, which are not against the virus, but against the harmful molecules and protect. And there's evidence that that can occur, at least experimentally. And there's evidence that a thing we call cytokine storm, which is a hyper-exaggerated, overabundant immune response, may well be the cause of the pulmonary disease that you see in COVID-19 and you saw in SARS, and you see in Hong Kong virus as well, and influenza as well. So that's another way you can limit the virus. So remember, the vaccine will work against people who haven't gotten the disease.
Absolutely. So we still have challenges, both administratively and also scientifically, to get this in control. And I know we are still going through this crisis, which is almost a calamity now. But I can't stop to think that this virus will mutate, and eventually there's going to be another one that will come down the line. What can we do now? Or is there anything we can do now? I'm sure we can. That will prepare us better for the next one.
They're testing a variety of antivirals, number one. Number two, they're able to sequence the virus from the time it was first picked up as we go along with the virus. And they have found very little evidence that there have been mutations, but these mutations have led to other viral strains, like you see with HIV and influenza. There's no evidence for that yet, and we have the ability to quickly sequence.
So is there anything we can do better to prepare next time when we get another viral epidemic like this?
Yes, we can. And as we have surveillance systems that are set up and work, and we support science, and we're able then to confront it when it first starts. That we don't deny that it's there. That we have politicians follow the requirements, of public health workers, what have to be done. Look, if your car was broken, you wouldn't take it to me to fix the car. You take it to a mechanic. And if you have a disease that breaks out, you take it to the expert in disease. And if you have a political solution you need solved, or an economic solution, you take it to economists or somebody like that. So use the expertise that's available, and make sure there's enough expertise around that you can work with it, okay?
Thank you very much. We have been speaking with Professor Michael Oldstone, and the author of Viruses, Plagues, and History, Past, Present, and Future. Thank you very much for your time and your comments, and we will be looking forward to your revised edition of the book that's coming up as well, that includes COVID-19 related issues as well.
Right. Thank you for calling.
Thank you.
Bye.